Yeah, I'm not sure, is this visible, or should we dim the light in the front? I hope that some of the next slides will be a bit more clear, but yeah, let me know if this is not working. We can probably try to dim this. Okay, so I've been asked to talk about CMB physics, what goes into the CMB anisotropies and these kind of things. And usually I would start like, yeah, this is work I've been doing over the past 5 years or whatever, but this is actually things I haven't been working on very much myself. So interrupt me if something is not clear. It's also the first time I'm giving this lecture, and I'm very afraid because it's being recorded, and there will be proof that everything is wrong what I said. So let's hope this is going to be okay. So I'm going to try to explain, as I said, physics of CMB anisotropies, or CMB in general, and what are the interesting challenges people are looking at now, and what are the future kind of things you might be hoping to probe with the CMB. So let me start with this picture of the history of the universe. For those of you who have been yesterday at the talk which I gave here, you have heard already. So this is the kind of standard picture which we now understand is kind of describing what the universe, the history of the universe looks like. Things started with a big bang, where there's an inflationary epoch where things get blown up from microscopic scales to macroscopic scales, and then the universe does barely nothing except for expanding in a radiation-dominated era. And you get here the process of recombination and the release of the CMB. And by looking at the CMB, we want to learn about the initial conditions of this universe and what sourced all the structures which are then forming in the post-recombination epoch. So this recombination epoch is some 300, 400,000 years after the Big Bang, and we have the universe. We know that it's something like 14 billion years old. Okay. So the big questions, I mentioned some of them already, are what is the universe made of? What are the initial conditions? Where do all the structures come from, and why do they look like they look? All these kind of aspects. Of course, we know that there's dark energy and dark matter, puzzling components of the universe which are really, really dominant. We want to understand about this and want to learn more about this, of course. Gravitational waves. Are they around? How can we learn something about the presence of gravitational waves in the early universe? It would be already a Nobel Prize just detecting them, right? So it's great. And what is physics beyond the standard model, of course? Those are also some questions. Of course, dark matter and dark energy go beyond the standard model. We understand that. But I'm talking about, variation of fundamental constants, or some particles which are around in the universe which we have not thought about, and all these kind of things. I will mention at the end something related to the neutrino number. Number of neutrinos normally should be something like 3, because we have 3 neutrino species, but there's indications that actually there's more neutrinos around, or more relativistic degrees of freedom. So these kind of questions are interesting and puzzling. And of course, the cosmic microwave background is one really excellent tool to learn about this. And you guys probably have seen this map. This is the all-sky map from Planck. It looks very similar in some sense, except for the color scheme to the map which WMAP was producing a couple of years ago. And there's these tiny fluctuations in the temperature, really, really small fluctuations of the order of 10 to the minus 5, 10 to the minus 4, perturbations in the different directions on the sky. And by looking at the statistics of these maps, we learn about the initial conditions and all these kind of things. And how that works is something which I'm going to try to explain during the lecture. But I wanted to go through a few things which are results or consequences of these studies, so that we know where we're going. And I will try to come back and explain a bit more where we have learned this from. So here's the power spectrum which the Planck folks released in this year, in May, and we now are probing, down to very, very small angular scales from the whole sky, basically, except for the monopole. We're measuring the whole sky and know the anisotropies on the whole sky at different frequencies in many bands, and we go down to a very, very small fraction of a degree, 0.01, 0.07 degrees. And this power spectrum characterizes the map, what is the information content in this map. It's a huge compression, because these pixels which you have here, it's a huge number of pixels. If you would want to analyze, do cross correlations on these maps, you would be facing a huge problem. And just converting the information which is collected to make these maps, converting that into actually these temperature maps is already a really big hassle. You have to really work hard to do this. But then you can further compress everything into these power spectra, and I will go into details what this means and so on. But you can extract then from this power spectra, you can extract information about the universe. And some of the information or some of the things we have learned, here's the WMAP power spectrum, just for comparison. You can see it goes up to L of 2000, which, this is roughly here. Planck is going a bit farther down to, L of 3000 in this range. And you can see that the number of peaks which Planck really constrains very well is, of course, larger than the number of peaks that WMAP is constraining. We know that the universe is made of 74% of dark energy, something we don't know what it is made of, but it's leading to acceleration of the universe. We have the dark matter component, something which is necessary and inevitable because we need to form structures how they are in order to form them. Just from the cosmological point of view, we need this. And then there's all these things we are made of are just making up a very small fraction of the whole energy budget of the universe, today's energy budget. And then here is a table which summarizes some of the main parameters. I don't want to go into details here. I just wanted to say that this is precision cosmology. We're talking about percent level precision in these parameters, and it's not anymore order of magnitude. Yes, a factor of 2 here, and the Hubble expansion is 500 or 100, same. We're talking about precision cosmology. This is really amazing, and this has been driven by measurements of the cosmic microwave background. And of course, at small scales, you can do things, so at high angular resolution, you can do things from the ground with the South Pole telescope and Atacama Cosmology telescope. These guys have been really pushing the frontier down to even higher resolution, to L of, here the last data point is even, it's going beyond, well beyond L of 2000, 3000. And they are pushing more with future measurements, polarization measurements, which are going to go to even higher resolution. And in fact, their real power spectrum goes to far higher resolution, but the cosmological information, you're starting to be dominated by other things. So anyway, this is the combined power spectrum, WMAP, and ACT and SPT. And from this, you can improve your parameters, and you get very consistent and high agreement in the cosmological parameters. And this is shown here, where the different combinations, WMAP9 plus ACT plus SPT plus both of them, where the cosmological parameters like the baryon density, the cold dark matter density, the angular extent of the acoustic peak, and reionization optical depth, and the spectral index for the initial power spectrum and its amplitude, where they are, you can see that these curves, these likelihoods, are all kind of agreeing with each other. And finally, then, a summary of some of the main outcomes from the Planck parameter estimations. What is important here, this is a huge amount of information. I don't even want you to look at these numbers in detail, but there's so much information in these maps, and it will take a long time to just extract all that information. And whatever we are going to learn during the school, talk about the school, all the tools which you use to do analysis of these maps and so on, this is going to be, there will be a lot of work needed, and people have to be prepared for doing that work. So it's really great to have the school. Very important point. Planck results are, in very good agreement with everything what has been done before. There's of course a couple of small puzzles and so on, but there will be discussion over the next few. In next summer there will be another release. There will be more discussion on what is going on and so on. But largely everything is really, agreeing and falling into place very well. Okay, so I have been talking about some of the main things we understand about the universe. How do we get there? Just here's a roadmap. This is not going to be the final explanation, but this is the roadmap of it. So here is we have the map of the sky. Here I also indicate the polarization information. WMAP has released polarization information at large scales, and what you do is you decompose this map. Of course, a 2D map on the sky, very convenient way to just compress the data or to explicitly show what the data, what this map looks like, is do a spherical harmonic decomposition. It's a very simple procedure. And then the interesting thing is that these spherical harmonics, they have a statistics to them. You can talk about how are they distributed. And you can learn by looking at the statistics of these spherical harmonic coefficients in the different polarization, B modes, and so on. You can learn something by comparing with the power spectra about the parameters. Because these coefficients, they predict, they give you an estimate for what is the kind of estimated typical angular scale and at which you have most of the perturbation power. What is the typical size of things? And then comparing these theoretical predictions for given parameters of cosmology with what you can estimate from these maps, you can get estimates of what the parameters are. It's a rather simple procedure in that sense. But to do that, of course, just the CMB alone is not constraining all the parameters equally well. For example, lambda itself is not something the CMB can directly, without additional aid, measure unless you have very, very high precision measurements. Because lambda is actually a parameter which is just doing a projection effect, but that's degenerate with the curvature. We will talk about that a bit. And also Hubble, the Hubble expansion rate today is something you can much better constrain, for example, with supernovae. So you put this together in a joint analysis with other data sets. Like supernova, as I said, large-scale structure measurements, so baryonic acoustic modes, Lyman alpha force, lensing, all these kind of things. You put them all in together in a box, and you try to understand what the data tells you, and get the parameters out of that. Okay, so this is kind of the roadmap of what's going on. Of course, here I skipped one very important point, and I think Alberto or some other people will talk about this. These maps don't look like that initially. You have to produce them as well. So I should have added, but we're not going to talk about this here extremely much because what we're going to learn about is CLPICS. We're going to learn about CMB fast and CAMP in particular. We're going to learn about recombination codes, and we're going to learn about CosmMC. These are the codes which we're going to be looking at, and this is where they are fitting into this whole diagram. HealPix is dealing with those maps, but HealPix is not producing the maps. Producing the maps means take the data, which is time-ordered, and convert it into maps. And that's a very, very complicated procedure, which depends on every experiment and so on. So somebody who wants to learn how to do that, that's something which you have to do specifically from the experimental point of view. So here, foregons and so on, you can treat them again with maps as well, but foregons are one of the obstacles in producing these maps. Okay, so HealPix is responsible for handling the maps. CAMP and CMB fast, these were the standard codes which people were using traditionally. These are responsible for producing power spectra from the theoretical model. So you put in the parameters, you get power spectra out of it. One part of that is the recombination history, which is computed with RegFast, CosmoRec, and HiRec is another code, which we're not going to talk about much, but I'm going to mention it on Thursday in my lecture as well, which produce very, very precise, or try to reproduce the recombination dynamics very precisely, and get good input, which helps to understand how to do these calculations for the power spectra. And CosmoMC is a sampler tool, which is just exploring the many-dimensional parameter space and trying to get the joint analysis done so that you can understand what the parameters are underlying the measurements. Okay, so let me just point out a few references. This is theory of CMB anisotropies. Sachs-Wolf. I found some pictures of these guys. This is Rainer Sachs, and then Wolf. I unfortunately only found a very old picture of him, which is kind of present day probably. But this is according to what I found on Google. This is in 1968, so this should be close to the time when they published this paper on Sachs-Wolf effect. Then Joe Silk, in connection with the CMB anisotropies, the Silk damping. He's visiting Johns Hopkins frequently, so I immediately understood that this is him, although he looks very different now, I would say. Then Peebles and you. I didn't find a picture of you, but Jim Peebles is there, and then of course Rashid Sonyaev and Jakub Seldovich, who, these are the really important foundation papers of understanding what the CMB anisotropies look like. And I'm going to talk about several of their, conclusions and derivations. And then I think these are really, really good, and I used many of these to put together the slides. Really nice lecture notes and reviews. Wayne Hu has, of course, some other papers with Sugiyama and so on, which are doing analytics of CMB anisotropies and so on, which are really, really good as well. But I recommend looking at these in terms of giving the broad overview. And then, of course, Wayne Hu has an excellent web page where he has a lot of information. Some of the animated GIFs which I'm using are actually from his page, so I highly recommend you look at this page. It explains a lot of things very, very nicely. Okay, so physics behind CMB anisotropies. I just want to gauge how am I in time here. Oh, it's great. Okay, so let me start with a bit of CMB history and simple physics. So one of the important points to mention is that, of course, the CMB background, the cosmic microwave background, this photon field, isotropic photon field, is a very, very natural consequence of a Big Bang model. So people were kind of understanding this early, that there should be this radiation field. And when it was discovered, then it was obviously a very, very strong, considered a very, very strong confirmation of the Big Bang model. So it's really important to understand that this is one of the main pillars of our understanding of the Big Bang problem. And it was already discussed and invoked by people like George Gamow and Alpha and Herman in the very early times, in the mid 40s, late 40s. Just in order they were thinking about the problem of nucleosynthesis of light elements and heavy elements. The discussion was, are stars responsible for the element abundances, or is this produced in the early universe? Which are the parts which contribute? Can the heavy elements be produced in the early universe, for example? These kind of questions. And when they were thinking about it, they were, understanding that this is one important ingredient, because, of course, things are driven by this thermal bath of photons. And Herman and Alpha in 1948, when they were actually at Johns Hopkins, I was really was interesting to see that on the paper. They were the first to give a rather good estimate of the CMB temperature, 5 Kelvin. Now, this is actually more like a coincidence, because first of all, they revised their value later, to 30 Kelvin, basically. And the main reason why they got 5 Kelvin, they estimated this just using, the understanding of what should be the temperature during BBN, and what is the current density of the universe. And they just did simple scalings, but the current density of the universe was actually pretty wrong. So it's a very big coincidence that they got this, more or less right, which is interesting. But then, of course, the CMB was discovered experimentally in the mid-60s by Pensas and Wilson, and you will see this medal popping up a lot of times. They got the Nobel Prize for this in 78. And the interpretation of this, signal, which they were not understanding, as a cosmological signal, was done by D.K. Pilbils and Roll and Wilkinson, where I took this figure from, where they indicate the thermal history of our universe. Here the scale factor, so basically inverse redshift, and here the temperature or energy density of different contributions. So the temperature of the CMB roughly scales like 1 plus Z. We all know this. And then here the radiation energy density scales like 1 plus Z to the 4th power, and the matter density scales like the 3rd power of redshift or temperature. And you can see here some features already. Here's the recombination epoch. Actually, a pretty good, it's kind of at redshift 1000 here. The radiation matter equality is actually slightly off because at that point they were not thinking too much about dark matter yet. Although, of course, there were already indications that dark matter could be around from other measurements, from clusters and so on. But in the cosmological model, this was not implemented yet. And those of you who look a bit carefully, the temperature of the CMB makes a small step here. And we see as well some interesting transition here, which just from the fact that electrons and positrons are annihilating and they're producing a lot of entropy, and the neutrino background is basically liberated from the dictation of the photon field and everything what is happening. So this is the kind of key features which they understood, of course, at that time already. Okay, so the first CMB anisotropy. Very simple. If you have an isotropic sky around you, just a black body spectrum, and you're moving with respect to this, you get a dipole. And this is just a Doppler effect. We all understand this. At lowest order, it is just a dipolar pattern on the sky where this mu is the direction cosine, just the direction of where you're looking and the direction where you're moving. So motion here towards this point that's where the hot spot is, and then on the other direction is cold. And I was actually, when I put this together, I was like, who actually came up with this? Who wrote this the first time? So I looked into this, and it turns out that the first who really explicitly mentioned the Doppler dipole in the CMB are Peebles and Wilkinson, slightly earlier than Bracewell and Conklin. This is the late 60s, after the discovery of the CMB. But probably the contemporaries already understood that this is going on, because there is this so-called Compton-Getting effect, which is related to X-rays, and you're moving with respect to this, so you should see a number count difference in terms of X-rays. So people understood, of course, Lorentz transformation and all these things. But the first to explicitly mention are these guys. The first, of course, this gives you a possibility to measure the velocity of us with respect to the CMB, which is interesting. I will later say something about the fact, because there is an intrinsic dipole which is expected from standard model as well, but this intrinsic dipole is so much smaller, and in particular also degenerate with this one. We have no idea how to subtract the intrinsic dipole from the motion-induced dipole, but there is a way to disentangle them by looking at the aberration effect, by looking at the change in the statistics of the CMB when we're moving. I will show a picture later.
I have a question for you.
Yes?
Do you know who discovered the dipole?
So the earliest, let me go through this. I will have it. So the earliest mentioning of the dipole as such is actually a bit earlier than these guys, 1 year earlier, Codon and Harvard, but they actually got the Lorentz transformation law wrong. So, but actually many results and really amazing discoveries are normally orders of magnitudes wrong initially. So in some sense, one should probably say that this is the first mentioning of this. Anyway, I mentioned already the primordial dipole. Just from there should be some intrinsic dipole, but it is a gauge problem. It's a gauge-dependent problem. You cannot gauge. You have the gauge dependence of the dipole, which is just from the fact that we are moving, and without doing something in addition, you cannot disentangle them. So nobody talks about it anyway. Plus, it will be anyway. Okay, let me not go too far. Okay, then there's the second-order effect. If you expand up to second order, you get a motion-induced monopole and quadrupole, which are small, because this beta parameter is over order 10 to minus 3. The temperature fluctuation from Kobe DMR is something like 3 millik. And there's also a Y distortion dipole, a quadrupole, and a monopole. So the mixing of black bodies, who was at my lecture yesterday, if you have different black bodies and you compare them, you're always in second order of the temperature perturbation, you're introducing a distortion. Okay, so some measurements of the dipole. First marginal detection, it's a 2 sigma result. If you look here, 2 point something sigma result, it's Conklin in 69. But the first really significant detection above 5 sigma was actually Smoot in 77. And people, of course, quote him for that as well. And what is interesting, so here's the evolution of the direction. So the direction was all over the place initially, and then it circled into this range. And the value of the dipole, of course, also has quite some large scatter. Initially, over the years, got better, and you got really high precision measurements with Kobe, DMR, and WMAP. And also one should mention Wilkinson and Penzias were, of course, understanding that even with their simple method, they can put an upper limit on the anisotropy of the CMB and then publish an upper limit on this on the anisotropy. But they were not looking just in general for the dipole, but just for anisotropy in the CMB in 67. One important point, the dipole anisotropy is, of course, it's very large, right? You want to get rid of it. And I said here, don't look here yet, but this is swamping the primordial anisotropies, so you want to get rid of it. But what is good, because you know the dipole so well, you can use it as calibrator. You can calibrate your frequency response, and this is something which is still done. Okay, so the CMB spectrum, the energy distribution, so not a function of angles, but you look at the different frequencies, is really represented very well by a black body with a temperature 2.725 Kelvin, very, very small, strong limits on spectral distortions. So for us, the CMB is just a black body, and there's a lot of interesting physics, and those of you who were yesterday at my lecture, they saw this. You have processes which actually can lead to energy release and distort the spectrum, and people have not, since Kobe-Firas, have not been pushing this frontier, but I'm at the moment trying to convince that there's a lot of interesting things to learn there. I'm not going to talk about this today, though. Okay, so then the discovery of the CMB anisotropies by DMR. This is their map, which they produced. Important points to point out, this is cold parts, the blue, hot is in red. The beam is something like 7 degrees, so it's a very low resolution map of the CMB, nothing comparable to what we have nowadays, of course. And here's just the measurement of the 2-point correlation function. I'm going to explain in 1 or 2 slides a bit more what this means. And they measured the large-scale 2-point correlation function with rather high precision, showing that there's rather low variance at large scales. One important point, and you heard this probably many times, but I just wanted to stress this again, parts on the universe which are here and here have only been in causal contact at very early stages. But at the time of looking at the CMB, these parts have not been communicating since inflation with each other. So it's a big miracle that the anisotropies are set up in the way that they are, very, very isotropic anisotropies, and that indicates that there was something like inflation. So these are causally disconnected parts of the universe. You could sell, you could take WMAP and say, this is a part of the universe, give it a name, and you can make money from this. In principle, you could do this, early part of the universe. I shouldn't have said that. Anyway, so consistent with the Harrison-Seldovich power spectrum, I'm not going to talk too much about inflation, the physics of inflation. This is, of course, laying down the initial conditions, and people are discussing this very heavily and want to learn about this. But in the early days, Harrison and Seldovich, they basically predicted that the perturbations initially should be gray. It's basically like noise on every scale, the same amount of perturbations, and it's scale invariant. And already from this measurement, from this flat, from the amplitude of the measurement, you can actually already understand that you need something like dark matter. This is of course a discussion which entered the problem just a few layers earlier, but just from the fact that the amplitude is so small, if you want to grow the structures we see today, you need dark matter to do this. And the large scale fluctuations, they are actually super horizon fluctuations at recombination, so they are really looking directly at the initial conditions and the effect of gravity on the CMB anisotropies. And this is where the Sachs-Wolf effect and integrated Sachs-Wolf effect come in. I will explain this. One important point, a hotspot is actually an underdensity. That's because the photons, they have to travel from this potential valve from the time of recombination to us, and they lose energy and effectively are actually feeling if there's a bigger lump from where they came that makes them colder. So this is interesting. Okay, I wanted to emphasize that there has been a lot of evolution in the angular resolution. So Kobe-Firas, this is the 7-degree beam map, 0.3 degrees, and then Planck, this beautiful high resolution map, which we are talking about. This is a dramatic improvement in what we, how finally we can map the sky. And I want to emphasize as well, of course, at small scales, this is a map which Amir Hajan was showing me when I was still at CETA, and he was really excited when he put this together. Look, there's clusters, there's point sources, and we see really, really high resolution primordial CMB. This is amazing angular resolution, nearly 100th of a degree, the beam. This is really impressive what technologically has been happening, and there will be more pushing in this direction. Okay, so I have talked about power spectra for a long time and two-point correlation function a bit. Let me do this, nutshell of this. So two-point correlation function, you're basically just asking what is the correlation of two different, temperatures. The temperatures are different in different directions under some angle, and you're asking what is the kind of correlation you have there. And you calculate that from the map. But if you want to talk about what people are talking about in the CMB community, they're looking at the power spectrum, which is in fact basically the Fourier transform of the two-point correlation function. So instead of talking in real space and an angle, you're talking about modes and wave numbers. And wave number, because we're liking to decompose this into spherical harmonics, we use normally the spherical harmonic coefficient as a wave number. And so the power spectrum dictates basically how at different scales, so this is very low L's or large scales, what kind of perturbation power you have there. So if you would downgrade the map to the Kobe resolution, you see this kind of stuff. That's just measuring the amplitude of perturbations here, fluctuations. If you go to the first peak, then that's what sticks out here. If you look at the map without doing anything to it, you immediately see here we have 1 degree patches. And that's where most of the power is. And then you have these higher peaks, which are also, of course, represented in the power amplitude you see. If you go only to the damping tail, you see that the fluctuation power is much lower in terms of the amplitude. The contrast is lower, but it's much smaller scale. So this is a hand-wavy way of understanding what this power spectrum means. It just indicates how much perturbation amplitude you have at a given, how much variance you have at a given scale. And for comparison, I found this really neat. The 1 degree is twice the diameter of the moon. So if you look at the moon and times 2, that's roughly 1 degree patch on the sky, which looks like here these tiny little marks. There's 40,000 points on the sky. We have 40,000 square degrees of that order. So the power spectrum describes the two-point statistics of the map. And in particular, if you have a Gaussian map, then this is enough to fully characterize the map. This describes all the endpoint functions of the map. And we will probably hear about this a bit more from Licia as well. But I just wanted to say that if you have a Gaussian map, you really can characterize everything with this power spectrum on average. And it's directly a reflection of homogeneity and isotropy that this is actually a sufficient thing to do. Because we understand that you should just depend on what is the scale, but not really on the direction. If you want to look at these kind of things, you have to look at the bipolar power spectrum, for example. That's something which people are using as a tool there. And I found this really interesting. Alberto, you maybe have not seen this. This is a nice picture from an early paper from Seldovic and I can't pronounce his name, and Sunyaev. And this is basically a first power spectrum. They talked about these anisotropies, and then they decided that they want to make a power spectrum of this, which is really nice. They even got the first peak right, but this was coincidence completely because they didn't put dark matter and nothing. So and plus the projection effects, all these kind of things are probably a bit different. But anyway, it's really, really nice that they understood that working in the power spectrum language is a very nice way to compress the information you have. Okay, cosmic variance is a very important aspect of because we have only one realization of the sky, right? We look at the sky and we can measure these ALM coefficients. But the power spectrum is really a statistical mean over ensembles of universes. This kind of statistical mean is something you cannot do with one universe. What you can do is you can use ergodicity. You can say by looking at the variance at different scales and averaging those ALM coefficients, which we have, we can get an estimate for the power spectrum. So if you take those ALM coefficients, you can write down an estimator for the power spectrum by just averaging them. Because every M should have the same cosmic variance, and you just sum all those M modes and get an estimate for the real power spectrum. But that means, for example, at the larger scales for the dipole, you have only 3 numbers, right? A, L equal 1, and M minus 1, 0, and 1, right? If you average 3 numbers, then that means that the error bar, like square root of n, is not very, very good. And because the map is actually real, you only have 2 independent numbers, A 1, 0, and 1, 1. Because the map is real, the other one is determined. That means that on average, the error bar you get by such kind of averaging is actually square root of 2L 2 divided by 2L plus 1. So that means that there's large variance in terms of the precision you can have when you're comparing the statistical prediction. There's large variance, which you cannot avoid. So this is very important, and at small scales this variance becomes very small, so that means at very small scales you can actually have very strong constraining power. Okay, some physics of the CMB anisotropies. Primordial CMB anisotropies and secondary CMB anisotropies, I'm going to talk about these two. I put here a line. This is actually a bit, some people consider some of these anisotropies, for example, from reionization, the optical depth effect, they consider that as a primordial, but some people say this is not. And primordial, I'm talking about the high redshift universe perturbations, so things which are driven by motions during the recombination epoch and by gravity. And then anisotropies secondary, the Sunyaev-Selvich effect, lensing, patching, reionization, all these things. Okay, so here's a nice picture of these perturbations, how they are growing in some of the first calculations of Selvich and Sunyaev. So you have this photon baryon fluid, they are tightly coupled, and they are because of gravity and because of pressure, photon pressure, they are performing oscillations, acoustic oscillations. And depending on what mass scale you're looking at, basically what length scale you're looking at, these modes, they grow in different ways. Because the Jeans mass determines when a mode goes unstable. So unstable is above this Jeans mass. This is the mass. And below it means stable. That means modes which are above the scale, they are just growing very, very slowly before they enter the horizon, which is determined by the Jeans mass. They grow very, very slowly, logarithmically, in fact. And when they enter the horizon, when they are going below the Jeans scale, they start oscillating because the photon pressure is supporting these oscillations. So they're just doing these oscillations. And then when recombination happens, when the decoupling happens, the pressure goes away and the baryons can start falling into the potential wells of, at that time they didn't include it, but the dark matter potentials. And then what is interesting, already in this picture, you can see that all of these modes, they start when they enter the horizon defined by the Jeans scale, Jeans mass. They actually all start in the same kind of phase initially, but they are then oscillating because of the different wavelength. They are oscillating at a different number of times, and then at recombination they actually are in different phases. So they enter the horizon in the same phase, but at recombination they have different phases, and that leads to these acoustic oscillations. And the acoustic oscillations, this is basically what you would see at recombination if you just draw the amplitude of these different modes at different mass, and what is the amplitude. And you see immediately this kind of oscillatory structure there. In this calculation, they didn't include silk damping. This is the large scales, and this is the small scales. So silk damping, which I will explain in a minute, should erase the power at small scales. And you shouldn't see any of these oscillations. And one important thing, these early predictions in the 70s were saying, you should have temperature perturbations of 10 to minus 3 or even up to 1%, because they wanted to create the structures we have. By the time, when recombination happens, you have only so much time, and you need higher perturbations in order to create if you don't have dark matter. Something which people, of course, understood that you should add. Okay. So here's another indication. This is one of the nice illustrations from Wayne Hu. The gravity and pressure, they set up these oscillations. The photon baryon fluid moves in this, oscillations, and then when recombinations happens, the baryons just fall into the potential wells set by the dark matter potentials. And I mentioned that they all start with the same phase, but then depending on the scale of the mode, they are ending at recombination at different parts of their oscillation phase. And the first peak is a compression peak, which had only time to basically perform half of an oscillation, while the second peak performed the full oscillation, and then the higher harmonics are just a reflection of this. And the photon baryon fluid is characterized by a sound speed, which is because of the baryons, you have an effective mass added. So you have baryon loading. This is this ratio R which is just depending on the baryon density and the photon energy density. It's very small at high redshifts. It only is reaching % or 10% close to recombination, whereas it is really rather small at high redshifts. So at very early times, everything is photon dominated, and you don't need this. And you're just the sound speed is basically the speed of light divided by the square root of 3. And then the sound horizon, which is characterizing the scale here, is just the travel distance photons can travel in the co-moving universe. The sound can travel in the co-moving universe. Okay, so recombination I mentioned, and I will talk about this in detail on Thursday. What is important, the universe becomes transparent basically when the photons, when the electrons get captured by the hydrogen atoms into hydrogen atoms and helium atoms, and this defines how the electrons and photons decouple. And what is one important quantity is basically the visibility function, which determines what is the probability at a given redshift that the last scattering event has happened there. So you see this visibility function peaks at around redshift 1100, and that's basically where the CMB anisotropies are coming from. And the width of this visibility function will define how the physics of dissipation is working as well, and polarization. Okay, so I mentioned silk damping, and this is of course nothing else than the effect that when you're having the chance to diffuse around as a photon, when you're just performing a random walk, that means that you're traveling from your initial point to some final point in a random walk, and you're erasing perturbations. You're basically like mixing photons by the scattering events of Thomson scattering, which is, you all have seen this formula. It's just coupling directly to the monopole, local monopole, and the quadrupole anisotropy. And because of how the quadrupole and monopole are working, you're getting erasure of these perturbations. And this is kind of illustrated here, where you start initially with some perturbations, and then after a few scattering events, you're already starting to smear out the perturbations. That's silk damping. And in terms of the transfer functions, photon transfer functions, I didn't go into much detail, but the calculation is, of course, a linear calculation, because we are talking about very small perturbations. And when you have a linear perturbation, you can do a Green's function. So you just give, for a given mode amplitude, you can evolve how the mode from the initial condition is evolving. And this evolution is described by the Green's function, or the transfer function as people call it. And the photon transfer function for a mode of very small scales, in fact, of very small scales, the larger this number, the smaller the scale, is actually, you see that this is roughly where the horizon is. Outside the horizon, not much happens, and then when it enters the horizon, or is close to the horizon, it gets this boost by gravitational decay, and then the oscillations are going on. Initially at a constant amplitude, because photon diffusion is not very efficient. But once the scale, because the mode is of course expanding, and the scale on which it is living is changing, once the scale hits the dissipation scale, the perturbation goes away. And that's the silk damping, which you can describe by this exponential cutoff in the transfer function. Here's some rough estimates for how this looks for the radiation-dominated era. It's a very small scale, and it's normally typically of order 100 times smaller than the horizon scale. So this is where things enter the horizon, and then roughly when the scale factor has increased a factor of 100, it's roughly good. Then you see that this cutoff is coming, and that's if you now would change this scale, you would see that this is working very similar for all kind of different wave numbers. And this leads to the mixing of black bodies and spectral distortions. I mentioned this yesterday for those of you who were there. Okay, so the effect of baryon loading. I mentioned that the sound speed, because of baryon loading, is getting lowered. If you have more baryons, you have a lower sound speed. But also, what is interesting, the effective mass of the oscillator is, of course, increasing. And this is kind of when you start with the same initial condition. We all understand that when you're just letting a harmonic oscillator, the 0 point is shifted. And the extension to which the oscillator goes is larger. The 0 point is shifted. And that leads to what you need there. It's very important to mention. You need dark matter. If you don't have a potential in which you're feeling this drag, this extra weight of the effective photon baryon fluid, you don't have this effect. But if you have dark matter around, then more baryon will lead to, going deeper into the potential wells and doing performing the oscillations deeper in the potential well. And this is something you can see here. It's again the monopole transfer function here with the gauge dependence included. And you can see that when you have no baryons, you just see these oscillations, and silk damping should at some point, like I explained before, should cut off things. But when you now include baryons, you see that the peaks are alternating. One is higher and one is lower. And this is just reflecting this kind of extra shift in the 0 point. And when you include too many baryons, or even more baryons, you even see that there is no change in sign anymore, because this is the absolute value, and it's in one time it's slightly below and above. At some point, you're shifting so far that you're just performing oscillations around the 0 point without changing the sign anymore. So this is something which is reflected in the peak structure, and I will show this later in the power spectrum. And then the Sachs-Wolf effect. This is a picture from their paper. I found this really nice because the perturbations at the last scattering surface here, the Thomson scattering is what they say, what is the last scattering surface. You can think about this perturbations in the gravitational potential. You can think about it in one constant time slice. Then you see these perturbations, these wrinkles in the amplitude. Or you can think about it in constant time, as a perturbed time. You will see that the effective redshift from different points is different. And that's exactly what the Sachs-Wolf effect is. It's gravitational redshifting. So you're feeling how much potential difference you had to travel through from the point of release of the photons until today. And that gives this, minus 1/3 of the potential as a temperature perturbation, effectively. When you're when you're looking at larger scales, this is the dominant effect. So Kobe-Firas, I mentioned already, that's the largest scale, super horizon. It's just the gravity. And that means that the hotspots, and I mentioned this, are corresponding to underdense regions because of this minus sign, basically. Okay, and then the integrated Sachs-Wolf effect, this is in principle the same source. It is gravity along the line of sight, but in this case, you're actually changing the potential. So you can see there's this potential well, it has a particular depth, and then as the universe expands, in this case, because of dark energy, because in the matter-dominated era, the potentials don't decay. The gravity pulls things together, and Hubble flow pulls things out in the same way, so that the potential is effectively constant. But when you have radiation domination or a dark energy domination, you get this evolution of the potential, and that means that the potential well gets shallower. That means when a photon comes in from behind this potential, it has the blue shifting when it falls in, and then the red shifting is not as severe. So you win net energy. So at the end, you're ending up with a perturbation which is coming from this ISW effect. And this is just a rough estimate how this works. You need to include both Newtonian potentials there. This is a Newtonian gauge, but I didn't want to go into more details there. Okay, and then the Doppler effect is also very important. We have the motions of the atoms of the fluid elements at recombination, and like in the case of our motion with respect to the CMB, we see a Doppler effect, and that Doppler effect leads to a temperature perturbation. You can define the minus or plus direction in a different way than you have a minus. I define it so that when the volume element is coming towards us, of course we have a positive effect. But normally there's a minus sign here. The important point is that in the tight coupling regime, so well before recombination, when the anisotropies are on extremely small scales and things are tightly coupled, the effective dipole is really vanishing. So the photon dipole equals basically the motion, is compensating the motion of the baryons. And in that case, the coherent addition of the photon dipole with the photon monopole, because it's basically two solutions, it's the cosine part and the sine part of the transfer functions, they actually give effectively zero oscillations. So one should not see these peaks, but it's very interesting. These peaks are restored because, of course, the baryon loading affects the dipole transfer function and the monopole transfer function in slightly different ways. So you don't get this cancellation. And then in addition, because of the free streaming phase, When you're looking at this last scattering surface, at some point photons are just free streaming to you. A dipole pattern free streams in a different way than a monopole pattern, and you don't get this cancellation and restore these kind of effects. So it is there. So the acoustic modes, acoustic peaks, they are also having some contribution from this Doppler effect, and I will show the separate contribution in a second. And, oh, there it is. So the sum of effects, this is the total sum, the power spectrum, with the first peak, second peak, and you can see already these kind of things, which are the comments which are made that, you know, the second peak and is a bit smaller than the first and so on. I will go into this a bit more. If you just take away, except for the acoustic oscillations, so the monopole and the integrated the Sachs-Wolf effect, in fact also integrated Sachs-Wolf effect, if you only plot those, then you see that the power spectrum would look like this. Sorry, the integrated Sachs-Wolf effect is also separated. Because of the Doppler effect, you get the curve which is here in this blue or cyan, which is slightly phase shifted because it's coming from the motions, and that's just reflected in the transfer functions. They are, you know, basically derivatives of the monopole transfer function. And you see that the Doppler terms, they of course are contributing to the power spectrum, the total power spectrum, especially here at the close to the first acoustic peak, but then also at the lower peaks. And then the integrated Sachs-Wolf effect, so the effects coming from the change in the potential, at large scales, this is dominated by the late times. This is coming from the evolution of structures during the dark energy dominated phase. And then at the, you know, close to the first acoustic peak, that's actually coming from the recombination epoch, because during recombination there's still a small amount of radiation, and radiation means that you have the slight imbalance between growth of structures and expansion. That means you're getting a net effect in change of potentials, and that's called the early integrated Sachs-Wolf effect. So these are all contributing to the shape of the power spectrum. So main dependencies on parameters. The power spectrum is sensitive to the curvature of the universe, because the first acoustic peak is a standard ruler, and also the other peaks. They are a standard ruler. You know how much photons have traveled given the time of recombination. You can then estimate, by looking at the characteristic angle you have on the sky, you can estimate what is the total curvature of the universe. Because in an open universe, you know, the peaks, the acoustic fluctuations should be slightly smaller. This is a flat case. This is the case we have. And then the closed universe, you have slightly larger patches. And here it is just depicted how when you change the curvature parameter, when you go from very small curvature to higher curvature, you see that the positions of the peaks, they are shifting to larger L, which means smaller scales. And this is, yeah. So, yeah. Position, okay. Okay, yeah, one important point is that there's a geometric degeneracy, because you need to actually understand what is, especially lambda, the dark energy contribution, leads to, of course, changes in the projections of these anisotropies. And this is something the CMB is not directly sensitive to, but changing lambda, and that's also shown here roughly, also changes the positions of the peaks. It also changes, of course, how the late integrated Sachs-Wolf effect is going. So there is some way to do something, but at large scales we have cosmic variance, so we're not actually having so much power in discriminating these things. So there's the combination of data sets which is really important. Okay, so the effect of Biomes. When you increase the baryon content, that decreases the sound speed, because the baryon loading was going in the denominator of the sound speed. This decreases the sound horizon, because of course when you have the sound speed smaller, your total time is the same. You're not traveling as far, and that means the positions of the peaks shift to smaller scales. You can see this if you look at these peaks. You see that they are all, when you increase this, they all move over here, right? Smaller scales. Then the other effect is the scattering rate increases. If you put more baryons, you have more electrons. That decreases the damping scale, and that means that silk damping, is moving to smaller scales. That means your power goes up. You can see this when you increase the baryon number. You know, decreasing it, you see, it should have been exponential. You would have seen very, very clearly that, when you have very low Bayer number, the damping is more. Now it's low, and then when it's high, you get a bit more power at small scales. That's actually a way, another ruler, because the damping scale is depending directly on the Bayer number. So it gives you another completely cosmology independent probe, like the standard, like the acoustic horizon. And then the last point, which I explained explicitly in one of the previous slides, the 0-point shifts in the dark matter potentials, and you get the change in the peak heights, alternating peak heights. The compression peaks are slightly higher. The first peak is higher. The third and fourth, they are slightly higher when you have larger Bayer loading. Okay, then the power spectrum parameters. How much time do I have? No time.
Well, almost.
Oh,
5 minutes.
My lecture is
10
at least.
maximum.
So I'm crucified. Okay. What is okay? Maybe this parameter. It's rather well explained. Maybe you can look at this. As the curvature modes is very interesting. The initial conditions, which I was talking about mainly, was adiabatic modes, where things start with a perturbation in the photon fluid, and then they enter the horizon, do oscillations and this stuff. But you can also set up entropy or composition perturbations, where you actually change the local ratio of baryons to photons or neutrinos to photons or these kind of things, depending on what kind of isocurvature mode you want to look at. Observations say that these are very small, but it's very interesting that these, in principle, can be set up in the initial stages. So it's good to look at. And you can see that the peak structure is different in this case. Secondary polarization is really important. It's produced by scattering. And there's one of the most important aspects that you have two polarization modes, the E-mode polarization and B-mode polarization. B-modes cannot be produced by linear order perturbation theory. That means that when you look at B-modes, you're actually looking at things which are either higher order in perturbation theory, or they are coming from the primordial universe, from gravity waves, or things related with lensing. The power spectra here, this is the picture which I showed very initially. Here's the temperature power spectrum, but then you have, of course, all the cross power spectra, the temperature and E-mode power spectra, the EE auto power spectra, and the B-mode power spectrum. And here's the lensing contribution. And people are, of course, trying to look at the B-mode polarization, because that's an indication of gravity waves, and you can probe the scale of inflation with this. Which is a very, very interesting thing to look at, and there will be lots of progress in that direction. Planck, Lightbird, Spider, they are about taking data, and maybe some future missions like Pixie, Prism, or Stage 4. Lensing effect, you have the growth of, you have these structures, the last scattering surface, photons don't travel on a straight line, that deflects them, obviously, and here's the one very important point, the intrinsic CMB, the lensing of when you put just a lump of matter, a potential perturbation, you see that the lensing, the E-mode polarization, you get a distortion. This is the temperature map, this is the E-mode polarization, and this is now this lensing potential which you put. Then you see the temperature map gets the deflection angles. You see this structure changing there where the potential is. You see E-mode changing, but there's also conversion into B-mode polarization, which is really important. You are producing E-modes from B-modes from E-modes. So looking at small scale E-modes is actually a way to learn about the structure of the universe, the matter in the universe. And here's one really, really exciting measurement which has been published very recently. The SPT folks, Duncan Hansen, he was for the first time showing that there is this lensed E-modes. He didn't get the absolutely direct detection of the auto power, but what he did is he used the measured E-mode, and he used data from Herschel, which is large-scale structure data, and produced potential maps, predictions for the potential maps. Then by using these two maps and putting them on top of each other, calculating what is the lensing effect, he made predicted B-modes from this. And these predicted B-modes then were correlated with what they measured in the B-modes. So they could, in this cross power, prediction plus what they measured, they could actually get a 7 sigma detection of this lensed E-modes, which is pretty impressive and very, very, very nice. It's very small scales. We're talking about L of 2,000, 2,500, And then the Sunyaev-Seldovich effect, it's coming from the scattering of photons in the hot plasma of galaxy clusters. The thermal motions, they just lead to this upscattering of photons. Yesterday I explained this quite a bit. If you plot this as a function of the intensity, you see this is the characteristic shape, the solid black line, thermal as set, and here's the null at 217 gigahertz. This is something which people are using to probe structure formation, and there's a whole industry of experiments in this direction. And if you also are allowing the cluster to move as a whole, you get the KSZ effect, where the most important part is the line of sight projection of the velocity. And this is a thermal shift. It's like the Doppler effect for the anisotropies. So you're just having the moving parcel of scattering medium, and you get a Doppler effect. And the temperature perturbation is not showing up very well. It's just this kind of shape, which actually has a maximum where the thermal asset effect is 0. So you guys have probably heard about this. And it allows you to look at things like, as I said, growth of structure, but also the gastrophysics, as Dick Bond loves to say, the gastrophysics of clusters. And it also depends on the large-scale flows. So you're actually learning about the large-scale flows by looking at this. This is an advertisement of one of the works I have been doing with my code or with my package. You can actually calculate the Z spectral distortion, including all the relativistic corrections, higher order temperature terms in a quasi-exact way without having any problems with convergence and so on. It's a package where you just put the parameters and you get out these spectra. So it's very easy to calculate. And it might be interesting for future high-resolution mosaicing of clusters and analysis of this. And for example, one of the interesting things to do with Planck is use the tons of clusters they have and do stacking analysis. Stack them up and, for example, look at the relativistic correction by stacking all the clusters and getting the average temperature. Okay, the secondary CMB anisotropy is just summarized again. So here we have the temperature power spectrum. We have the integrated Sachs-Wolf effect, in particular at large angular scales, small L's. There is the integrated Sachs-Wolf bump as well here, but this is just the late time integrated Sachs-Wolf they looked at. Lensing leads to smearing of the anisotropies, so you get this small changes. There's a Ricciama effect, and here are here are some scattering related effects. Ionization leads to suppression of power, and you get some generation as well. Okay, and I'm not going to talk about this then, but I'm going to say something about this. This is cool. This is a lot of fun stuff which you can do with those maps, for example, from Planck. People have been looking at directly reconstructing the lensing potential, and this is an amazing measurement of the lensing potential at different L's, and this is even a map of the lensing potential. So they used the data, they used higher order statistics, and reconstructed what kind of intervening matter you had in order to get the statistics changed in the way they are. Because when you have the effect of lensing, this introduces some sort of non-Gaussianity as well, because of nonlinear structures and all these things. It's very interesting. And then there's this effect of motion. When you have the isotropic sky and you're not moving with respect to it, you look in all directions and you should be statistically isotropic. When you're moving, you get due to aberration, light aberration. This is at, I believe, 90% of this is probably 50% of the speed of light. I don't remember. But you see that it leads to a magnification of structure in the direction backward of you, and it leads to some focusing of structure at high in the direction where you're moving. That means you're breaking statistical isotropy, and that effect is distinct from the Doppler effect, from the motion-induced Doppler dipole. So you can, in principle, by looking at this change in the statistics, you can learn about the intrinsic velocity you have without relying on the dipole. And that means you can actually get at the intrinsic dipole. It's interesting. And there's lots of things people are discussing: non-Gaussianity, topology of the universe, CMB anomalies, power symmetry, all these kind of things. This is all exciting work which will be pushed and done more in the future. Here's this huge catalog of galaxy clusters. As I said, stacking analysis, all these kind of things can be done. Really interesting. So I think I will just end here then. I'm sorry that it took long. I had only 50 slides, and normally I have more, but okay, I was talking more. CMB physics is very rich but also very clean. It's very simple physics. To some extent, you can't get simpler. And that allows you to do calculations at a very high level of precision, which of course means you can extract a lot of information by doing very precise measurements about the universe. CMB anisotropies so far have provided a really outstanding confirmation of lambda CDM, cosmology. And the data is now so precise that one can actually look at non-standard extensions like, dark matter annihilation, things which are affecting the damping tail of the CMB. You can directly ask measuring the helium abundance, neutrino number, all these kind of things. And I think this is, a great proof that there is a bright future of CMB coming ahead, and also already we are living in that. Of course, in the present, we're having a lot of interesting things coming. And there will be many, many new avenues opening up. Polarization will be pushed very, very strongly from the ground. There might be something like spectral distortions measurements in the future. And those of you who were there yesterday, I think this is really exciting. There's high-order statistics one can look at, cross-correlation with other data sets. One of the examples was Herschel data with the E modes and producing the B mode, lensed B mode, and then getting cross-correlation. That's one of the kind of things which are going to be possible in the future and will be pushed more, which is really interesting. And I think this proves that there will be a lot of work for you guys ahead, and you should really enjoy this. Thank you.
All right, I think so we can have a few questions, and also encourage you at coffee break and lunch, join the lectures.
Oh, but is there no coffee break? I mean, we have to skip it, right?
Yeah, we have another lecture.
Because of me.
Before coffee break. So is there any question now? For Jens? If you prefer to talk to him at coffee, that's also right. But anyway, so it's perfectly clear to you. So I see. Good. That's great. Okay, I will not push you hard. So I hope that by the next lecture you already